Are you sick and tired of doing matrix multiplications the hard way? What if I told you that our top scientists have figured out a new method?
Strassen?
No, not quite.
Moosbauer-Poole?
Actually, that's already old news. Get out your pencils and computer chips. We're taking a look at a new algorithm from the Institute for Algebra in Austria.
Yay! Hi everyone! Today I want to talk about something that's massively important in LLMs, in graphics, even in high-frequency trading. Today I want to talk about matrix multiplication and explore brand new research in finding optimizations. You might also be extremely surprised to know that we still do not know the minimum number of multiplication operations required to multiply two different matrices. If you have one matrix, which is size n by m, and another which is size m by p, for each of these different values, the optimal strategy for multiplication actually changes for every single different size. Before we jump into bleeding-edge research of matrix multiplication optimizations, let's take a step back and look at some of the historical background. Probably many of you at some point in your life have multiplied two matrices together, and you've probably done this by hand using the naive approach. The naive approach is very simple to understand from a human's perspective, but it's also very inefficient, especially as matrices grow and grow exponentially larger. Let's take a look at this quick example. We have two matrices, matrix A and matrix B, and for our n and m values, the number of rows and columns in matrix A, that's a 2 by 2 matrix, and then for our m and p values, for matrix B, that's 2 by 2 again, to compute a 2 by 2 matrix C. Let's start our animation and take a look at this. Very simple, we're taking the dot product of the first row of matrix A with the first column of matrix B, and then that becomes the first element inside of matrix C. Similarly, we have the first row of matrix A applied to the second column of matrix B, getting our second element in C, and then we can continue on to get the entire value of matrix C. But you'll notice there are actually 8 multiplication operations required to compute the value of matrix C, and this is just the simple, most base case for multiplying two matrices since they're so small, size 2 by 2. And actually, the rank or number of multiplication operations required to compute these two matrices is 8 here. Now picture this. The year is 1969, and up until this point, everybody's been using the naive approach for matrix multiplication. This actually runs on big O of n cubed time complexity, and if you're a programmer, that just kills you to hear, but nobody knew better up until this point. And in walks Strassen with a brand new method for multiplying two matrices together. Let's take a look at the animation for multiplying matrix A, again a 2 by 2 matrix, with matrix B, another 2 by 2, to compute matrix C. Now Strassen came in and he changed the order of operations for computing these and decided to multiply these and calculate them into sub-blocks first. You can see we're calculating all of these different m blocks right here, and then we're taking these final products to add them together to compute the final matrix C. Now this actually is able to reduce the rank, which is the number of multiplications required, by 1 for a 2 by 2 matrix. That means that we now have a rank of 7 instead of a rank of 8. That might not seem like much, but if you start to think of the exponential increase in matrix sizes, this will actually decrease the rank of the multiplications by a significant amount. Now, if the naive approach ran at big O of n cubed time complexity, the Strassen method actually runs approximately at big O of n to the 2.807 time complexity, and thinking of that again in exponential terms is going to be a significant reduction in time complexity. You might be thinking, perfect, now we have the Strassen methodology, we never have to have the naive approach again, and we can completely get rid of that terrible big O of n cubed time complexity. But that's actually not the case. If you remember, I mentioned in the beginning that there's very specific optimization strategies for every single different size of matrix that needs to be multiplied. Now, Strassen actually falls prey to this issue as well. It only works best under certain circumstances. It only works best for matrices that are square, and it actually works optimally if the matrices are a power of 2 size as well. Not only that, but we got rid of one multiplication inside of our 2x2 matrix multiplication, but we actually had to add 4 additional additions to computing those matrix operations. So it's kind of a trade-off here between multiplication and addition. One thing you might not be aware of, though, is actually multiplication is more computationally expensive to perform than addition or subtraction operations. We've seen the naive approach, and we've also seen the Strassen approach in action, but now let's actually try to benchmark the two against each other so we can see the actual reduction in time complexity. Now, I have a GitHub that is available to you, and I'll link to it in the description of this video, and this demonstrates a lot of different matrix multiplication schemes that we're using. Here we have the naive multiply, and we also have the Strassen multiply. So let's take a look at our naive multiply. Let's do naive multiply.cpp. And this is just filling up some dummy values inside of 2 different matrices and then multiplying the 2 together and then calculating their output. And it's also doing a few different benchmarks so that we're able to see the actual time it takes to multiply these 2. You can see we're just doing this simple, go up here. We're just doing this simple multiplication between these two. So the naive multiply is extremely simple to be able to read, but you can see it does have that dreaded big O of n cubed time complexity. So let's go over to our Strassen. It's a little bit more complex, but it's really not too bad. So we have our Strassen.cpp, and you can see I'm just filling the matrices with dummy values. And this is actually going to include portions of the naive multiply up here, but it also has the additional addition and subtraction values. And remember, it's that kind of trade-off between reducing the multiplication number, but also adding those extra addition and subtraction. So let's run those two against each other. First, I'm going to run my naive multiply. You can see I've got a 512 by 512 matrix. I thought that would be large enough to be able to demonstrate the optimizations seen by the Strassen routine. And we've got 99.2859 milliseconds. So let's see what our Strassen does with a matrix of the same size. Let's do our Strassen multiply. And here you can see we do actually have a significant decrease in the amount of time it took to multiply those 2 matrices. And if you think about it in the grand scheme of things, the 512 by 512 matrix is still not exceptionally large, but it's one of the minimum values that you're able to see this major reduction in time complexity between the two. Now let's move on to the brand new research in the field of matrix multiplication optimizations. In this paper, Consequences of Moosbauer-Poole Algorithms, was actually just published in May of this year. So that's incredibly new research that is available to the world to now be applied to optimize our matrix multiplication. So the researchers here were trying to find the most optimized matrix multiplication for a matrix of a given size. So they're going through and trying to keep track of the rank, which is the number of multiplications required for those matrices, to be able to multiply those matrices together. And this is actually for any given value of NMP. Remember, those are the dimensions of the matrices, and so it's not limited to the square requirements that Strassen, for example, is limited to. So this is actually having to go through and calculate a specific optimization for every single specific size of matrix, no matter whether it's N or M or P that actually change in dimension. So it's very specific and computationally intensive work to be able to find this kind of optimization. Now, they actually used something called the flip graph search algorithm to be able to find and keep track of those ranks. So they have an entire paper on this as well. Let's look at a quick visualization. What they're trying to do is they're trying to keep track of the lowest rank possible as they're testing all of these different algorithms. So you see we start with a rank of 100 in this example, and we're keeping track. We've gotten our rank down to 95, so we need to keep track of that rank and keep on going until we have traversed the entire graph to find the lowest rank possible for a given dimension of two different matrices. This is very similar to other graph traversal algorithms, such as depth-first search or breadth-first search, for example, that you might be familiar with, but they're pretty much just trying to mutate the different algorithms for a specific size of two matrices that they're attempting to multiply and keep track of the minimum rank possible as they go. And you can even check the correctness of the different algorithms against other approaches, such as the naive approach, to ensure that the algorithm that you're working with is actually giving the correct result. And they do actually have an entire secondary research paper if you're interested in diving more into the flip graph search algorithm that they were able to use to be able to compute these values. To get into the fun part of actually using these matrix multiplication optimizations, you might start and click on their GitHub repository and then be extremely disappointed to find that it looks incredibly confusing. They have all of these arbitrary looking number folder names inside of here, and if you're like, okay, I'm gonna look inside of here, you can see these really scary .exp and .m files that look like these crazy long mathematical formulas, as well as this .m file, which doesn't really look like it means anything to humans, which it really doesn't. Actually, what this is doing inside of here, we'll go back to the root of this repository. These are the optimum algorithms for multiplying matrices of these different sizes. So the folder names here correspond to the n, m, and p values, which are the dimensions of the different matrices that are being multiplied. So if we pick one in particular, let's see, we have a 6x6 matrix and a 6x7 matrix, and we check inside of here, we can actually see the formula that is optimum for multiplying matrices of these sizes. So I recommend taking a look at the .exp file, since this is going to be more human readable if you're trying to understand the formula. But this is actually one giant mathematical equation for multiplying these two different matrices. So you can see how complicated this gets. You have to go through and apply all of these different addition, subtraction, multiplication schemes to be able to calculate the final value of the C matrix. But you can see we have our A matrix, and this is just showing the current row and column that is being added, subtracted, or multiplied in this occasion. And we even have sub-values of C that are actually getting calculated during this process. If you really want to torture yourself and you really want to go through and read the entire mathematical algorithm, I definitely suggest sticking to the .exp or the expression files, since this does actually show the expression in mathematical terms. But if you really want to torture yourself even more, you can go over to the tensor format file or the .m file, and these are actually equivalent to each other. It's just that the .exp file is going to be more human readable, and this is going to be more parsable to machines if you actually want to apply these formulas. And note that there might be multiple different expressions inside of each different matrix size. These actually have the same rank. There's many roads that lead to Rome, so there's a lot of different ways that you can potentially optimally multiply these matrices together. Now I've actually written an application that goes through and parses these .m files that are inside of the matrix multiplication repository for this particular research paper, so that you can actually apply the formulas that they're using and that are so new and cool. So you can run the formula multiply that's available inside of my GitHub repository, and then just pass in the path to the target.m file that you would like to parse and multiply matrices with. So this is just going to be using some example matrices to perform the multiplication to demonstrate how this can be used and performed. So pass in the actual size of the matrices that you would like to do. In this case, the folder also says the size, but you have to specify the specific size. And this is going to run some tests and see if we can multiply these matrices. Here we go. This is also giving a little bit of a benchmark. It only took 0.09 milliseconds plus a little bit more, and it did 183 product terms to compute the value of the C matrix between A and B. So you can see we have a 6x6 and a 6x7 matrix. Like I said, those n, m, and p values. And the final matter of importance is verifying that the actual outcome of the matrix multiplication is correct. And again, I really suggest using the naive approach to test any kind of optimizations that you're doing to verify that you're not just optimizing something to be incorrect, and you're actually optimizing something to correctly multiply these matrices. So if you would like to verify their specific algorithm, you can just run the same thing and then do -- verify. And this is going to perform the same thing, except it's going to run it against the same results for the naive matrix multiplication. And you can see verification successful. We're all good here. Let's move on to the most exciting portion of this. What are the actual results of these optimization algorithms? And they have all of the different ranks listed inside of the ARXIV paper, and they're applying these against the different naive schemes, plus the previous record for the minimum number of multiplication operations for matrices of given sizes. So they're tracking the size over here on the left. You can see our n, m, and p values for each different respective matrix size. You can't get away from those n, m, and p. They're gonna haunt you for the rest of this video. So we have our naive rank, which is going to be the most dumb, least optimal way of multiplying these matrices, plus the previous record for multiplying these matrices together. And I think some of the most impressive ones can be found down here. You can see they don't always find a more optimal strategy with their flip graph search algorithm, but they do often, for the most part, find these new optimal algorithms. You can see for a 5, 6, 7 NM and P value, we go from a previous record of 159 to the current record with this of 150. So that's 150 multiplication operations, cutting down by 9 total operations. And that's actually pretty impressive. They were able to compete with the previous records for not an insane amount of compute time here. Now, a few caveats for these matrix multiplication optimizations. First of all, Strassen really only pays off when compute, not memory bandwidth, is the limiting factor. Not only that, but if you're running on a GPU, for example, you really only see the benefits of Strassen when you're multiplying matrices that are absolutely enormous. This means that for most GPU ML workloads, you're going to be multiplying smaller matrices, so classical GEM or general matrix multiplication actually usually wins out here. However, if you're working with custom silicon, for example a TPU, you can actually bake in these advantages into the hardware itself. For example, if you're using custom silicon, the actual add operation size is physically smaller than the multiplication operation size. So even if you're having this kind of trade-off like with Strassen, where you have additional add operations, the actual overall size is still going to decrease. Despite some of the limitations, optimized matrix multiplication is extremely important in both the field of mathematics and in high-performance computing. And if you take a look at the research paper, the researchers actually only spent approximately 1 day with 100 CPU cores of compute thrown at this problem to compute each different matrix multiplication optimization for a specific size. That's really not that much in the grand scheme of things to further an entire research field. Now, if you think about it, you could potentially be the next person to compute the next matrix multiplication optimization. So now go compute some matrices. Lori wired out.